In this video, we are going to learn about periodic trends, including atomic size, ionization energy, electron affinity, and metallic character, primarily for main group elements. Let's begin by discussing the size of atoms. If we think of atoms as spheres, we can measure their size by measuring the atomic radius, which is the distance from the nucleus to the outermost electrons. If we look only at the main group elements, there is a clear pattern. As we move across a period from left to right, atomic size decreases. As we move down a group from top to bottom, atomic size increases. This means helium is one of the smallest atoms, while cesium is one of the largest. To understand why this trend exists, we need to think about where the electrons are filling. Across a period, electrons are entering the same shell. For example, the 2s and the 2p belong to the second shell. However, elements on the right side of the period have more protons in the nucleus than elements on the left. Because opposite charges attract, the increased positive charge pulls the electrons in the same shell closer to the nucleus, making the atom smaller. When we move down a group, elements have valence electrons in different shells. For example, lithium has valence electron in the second shell, sodium in the third shell, potassium in the fourth shell, and so on. Each additional shell is further from the nucleus, making the atom larger. There are some exceptions to this general trend, but those are beyond the scope of this course. Let's look at a practice question. Which answer choice lists the element in order of increasing atomic size? Option A, aluminum, phosphorus, chlorine, argon. Option B, rubidium, strontium, calcium, magnesium. Option C, nitrogen, phosphorus, sulfur, selenium. Option D, neon, argon, chlorine, bromine. Option E, hydrogen, helium, neon, argon. To solve this, remember that increasing atomic size means moving toward the bottom left corner of the periodic table. Option A can be eliminated because phosphorus is smaller than aluminum. Option B can be eliminated because strontium is smaller than rubidium. Option C can be eliminated because sulfur is smaller than phosphorus. Option D moves from neon to argon to chlorine to bromine, and each step increases in atomic size. Therefore, option D is correct. Next, let's discuss ionization energy. Ionization energy is defined as the amount of energy required to remove an electron from a gaseous atom. Consider a sodium atom. Sodium has one valence electron. When ionization energy is applied, that one valence electron is removed, forming a sodium ion and a free electron. The closer an electron is to the nucleus, the more energy it takes to remove it. As a result, large atoms have low ionization energy, while small atoms have high ionization energy. Atoms in the lower left corner of the periodic table have the lowest ionization energy, while atoms in the top right corner have the highest ionization energy. We can connect ionization energy to the electromagnetic spectrum. High-frequency electromagnetic radiation has enough energy to remove electrons from atoms. Ultraviolet radiation, X-rays, and gamma rays are called ionizing radiation because they can remove electrons from atoms in your body, causing damage such as sunburns. Lower energy radiation does not have enough energy to remove electrons. Visible light can excite electrons to higher energy levels, while microwaves mainly cause molecules to vibrate, producing heat. Electron affinity is related to ionization energy, but describes the energy change when an atom gains an electron. A high electron affinity means the atom strongly attracts additional electrons. Electron affinity trends are less regular, but in general, nonmetals have high electron affinity, excluding noble gases. This makes sense because nonmetals tend to form anions by gaining electrons. Metals have low electron affinity because they prefer to lose electrons and form cations rather than gain electrons. Here's a practice question. For each pair, select the element with the higher ionization energy, lithium or potassium. Lithium has the higher ionization energy because it is higher in the same group. Potassium or bromine. Bromine has the higher ionization energy because it is smaller and further to the right on the periodic table. Phosphorus or chlorine. Chlorine has the higher ionization energy because it is smaller and further to the right in the same period. Our final periodic trend is metallic character. To understand this trend, we need to recall where metals, nonmetals, and metalloids are located on the periodic table. Nonmetals are located in the top right corner above the staircase and have low metallic characters. Metals are located below the staircase and to the left. The closer an element is to the bottom left corner of the periodic table, the greater its metallic character. Metallic character refers to typical metal properties such as being ductile, malleable, and good at conducting heat and electricity. Here is a practice question. Arrange the elements in order of increasing metallic character: phosphorus, sodium, chlorine, and potassium. Chlorine and phosphorus are both nonmetals. Chlorine is further to the right, so it has less metallic character than phosphorus. Sodium and potassium are metals in the same group. Potassium is further down the group, so it has greater metallic character than sodium. Chlorine is the least metallic, followed by phosphorus, then sodium, and then potassium is the most metallic.